All right, so today we're going to be doing day 20 in Advent of Code. The first part of this challenge is that we get a map once again, and we have a starting position and an end position. And they tell us that there is only one valid path that actually leads from start to end. So knowing this, what they want us to do is to sort of cheat and jump through a wall, and we have exactly 2 picoseconds to do that, and each movement is counted as 1 picosecond. So here there was a hashtag. So if we jump through this wall with 1 and the second move, we have to end up on an empty space again if we assume that the hashtags are walls. And once we've done that, we have to shorten our length to the end by some amount. So in this case, we would be saving 12 picoseconds. And they have a bunch more examples. So if we jump from here to here instead, we don't have to traverse all of this side. So it would save a lot more. So it says that we save 64 picoseconds, which is a lot better. But what they actually want us to do is to save at least 100 picoseconds and to see how many different cheats could save us at least this many picoseconds. And we won't be using the sample grid. We'll be using the actual grid that we're getting as the input. And if I search for S, we can see that it starts somewhere here and E is somewhere else. So they're pretty close, but presumably they travel all around the map to be able to get to each other. And I've actually made some GIFs, so we can see that this is the sample one. So if we look over here, we can see that the sample one begins at the top and keeps going all the way around and then eventually goes to the end. And I've made this with Pillow. It was a great library. A bit hard to work with, but once you learn it, it works pretty good. I'll show the rest of the GIFs later. But let's go through the code. So the first thing that we want to do is to import deque, because we're going to be using a breadth first search to be able to find the actual valid path, because it's not given to us. We have to find it first. And then I'm going to read all of the lines from the input file. So I just copied the entire input that we got from the challenge and put it in this input.txt file. And for every line, I am going to append it to the grid. And we want to make sure that it's converted to the list and that we strip any weird characters. So this way, we will have a 2-dimensional grid with all of the different values that are here. And then we can access it with the rows and the columns, and we can get whatever specific characters over there to see. Is it a wall? Is it a dot? Can we traverse there? Is it valid or not? And to do that, we also have to know how many rows and how many columns there are. So if you have a grid and then you say length grid, it's going to give you how many different rows there are. But if you say grid 0, it's going to look at the 0th index and then see how many there are. So it's going to give you how many columns there are. Then the next step is we want to see where the start is. So we want to iterate through the rows and the columns in the grid and see wherever it's equal to S. So if we try to find the S here, it's going to be at whatever index this is. It's going to find it, and we're going to store it as the start, the rows and the columns. And once we found it, we don't have to keep going, so we can just break. Otherwise, if we didn't find it, then we continue. Next thing we want to do is we want to initialize the distances. So we're going to be making another grid, which is basically the same size. So if we imagine another grid, and we're going to be initializing it with -1. So it's going to be -1 here, -1 here, 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 everywhere. And it's going to be the exact same size as the actual grid. And we have this so that we can keep track of how much distance it is from the start. So if it starts in this corner, then this becomes 0, because we can see here we set the distance at start 0, start 1 is equal to 0. And we see that the start is just the rows and the columns. So at the index where start is, we say that the amount, the value, the distance, the picoseconds is 0. When we keep traveling, so if we go here next time, then this one's going to become a 1, this one's going to become a 2, and then it's going to keep traveling. So if we assume that this is the entire grid, once we find the valid path, if it's this shape, it will sort of leave a breadcrumb trail of increasing numbers. So this will be a 1, a 2, 3, 4, 5, 6, 7, until all the way to the end. And we use this to see how far along we are, because what we're going to do in the function to check the possible cheats is to check, okay, if we jump from here to here, is this how many points are here and how many points are here? If we see that we have 10 points here, so we've traveled 10 from the beginning, and this one is 200 somehow, then we know that the difference is 190. So we've just gained 190 points, and then -2 because we actually had to jump through the wall as well. So that costs 2 points as well. But this is the way that we're going to be checking if we can jump through a wall, and how many moves we saved by doing that, and if it's at least 100. But before doing that, we have to implement BFS, breadth first search. It would work with depth first search as well, but it's just more common to use BFS. So that's why we included deque, double-ended queue from collections. A double-ended queue is basically if you have a start and an end, and then you want to pop this index and then remove it. What you would do in a normal list or queue is that you would have to move every element by 1, which is very inefficient. So instead what we do is we just say, okay, you know what, if we remove this element, then just make the list this big. So just say that it starts here now. So and then we don't have to worry about this. So we can pop from the beginning and from the end. That's what's called a double-ended queue. And removing from either side is in constant time. So not O of n time, which is better. So the first thing that we do is we take the row and the column in the queue, and we pop left. So we remove the element that we've had. And the only element that we had to begin with was the start point. And when we keep traversing, we keep looking in every direction. So the only valid directions are going to be left, up, right, and down. And then if there's not a hashtag, so if it's not a wall, so if it is a dot, then we can travel here. If it's not outside the grid, so if this is outside the grid, then we can't travel there. So there's different conditions. We have to check if it's not out of bounds, as I've said, if it's not a wall, and if it's not already been visited, because then we already know where it is, so we don't have to visit it again. And this is what we do in here. These things are right here are just the different directions that we should check. So we have a for loop to do this for every single direction, for up, down, left, and right. So we have row plus 1. So if it's a row and if it's here, rows start from top to bottom. So if we add 1 to the row, it's going to go down. The column stays the same. So this right here means down. Row minus 1 means up. A row call plus 1, that means go to the right, and this one means go to the left. Then we check the out of bounds, which is right here in both the rows and the columns. We check if it's not a hashtag, so not a wall. And we also check if we haven't visited it. And if you remember, we initialized the grid with a -1. And the way that we initialize the two-dimensional grid is that we do it with a for loop for every row, so that they are not linked to each other. Because if we do not do a for loop and we just times it by how many we want, then they will be linked in memory, so they will have the same address, and then when you update one of the rows, all of the rows will update with the same value. But that's not what we want. That's not a true two-dimensional grid. So now that we've gone through all of these checks, and to see that it is valid to go there, we will take the new row and we will take the last distance that we had. So if we're at start, it would have been 0, and then we get 1. So if we traveled a single space to here, then it would be 1. If we travel here, we would take the previous one, so 1 plus 1, it would be 2. Then it keeps going 3, 4, 5, 6, and so on and so forth. And for every direction, if it's valid, then we append it to the queue, which is not really necessary because we know that it's only going to be one direction that's going to be valid, since there are not several answers that could be correct, several paths that could lead to the answer, because they said in the question that there's only one valid path. So we could implement this in a different way, but this is just the most common way to traverse to a grid with a BFS and a queue. So now that we have the traversal, let me show you the GIF. So I've made a GIF with a pillow, and it traverses all the way from the beginning, and it keeps going and until it finds the end. And this is not jumping through the walls or anything, but we can just see how it traverses. And if I go to the fast GIF, we can see that it actually takes up the entire map. So it's a very long path that it takes. So when it sees this wall over here, if it jumps, it's definitely going to save more than 100 points. So all of these walls over here, if we jump them, is definitely gonna save us 100 points or more. And then there's a lot more along the way. So the answer should be at least maybe 20 to 30. That's how many walls I'm assuming is over here. And of course there's a lot more in different places as well. So that's the visualization. So to check for the different possible cheats or jumping through the walls, we have to get the grid and the distances, and we call it over here, and it will just return the count, like how many different cheats we saw are possible, which we then print, and that's the answer that they want us to give. And what we do in here is we keep a count, of course, and then we iterate through the rows and columns. If we see that it's a wall, we don't even have to check it. But if it's not a wall, what we want to do, if I can delete everything here and not blind you guys, what we want to do is, if we have a starting position and we have two different moves that we can do, we can either go up and then up again, or we can go up and then left, or we can go up and then right, or we can go right and right. So these are the four different moves that you could do to be able to get somewhere across a wall. So here we could assume that the wall would be here if we would do this, or that the wall would be here if we would do this to go to any valid path. So these are the four different positions that we've made. So row plus 2 and then just column, or row plus 1, column plus 1, or row and column plus 2. So this one, and then this one, and then lastly row minus 1 and col plus 1. So technically one of them is under, but it doesn't really matter what order you put them in. It just matters that you have sort of half of it, and then the other half would be the mirrored version. So this would be, if we mirror it, we would get the other answers. But we don't actually have to do this, because let's say that there's a path that travels like this. When we check this one here, we only have to check the sort of this top half. And when we travel all the way down here, this one over here will be checking this top half as well, so it will collide with the previous path. So we don't have to check all 8 directions, we only have to check 4 of them, and then make when we calculate the distances, we use an absolute value. So if it's negative, it becomes positive. And we check if the difference is more than 102. So if the start was somewhere over here, and then we travel all the way to here and we get to 200, and if we jump, if we just check the top sides, then it's not going to find that there's a jump until it comes here. But here it will find that there is a jump, that it can be made, and it doesn't matter if it's backwards or forwards. We just care about what the difference is. So if this was at 0.5, then we have to keep in mind that where we are. So if this is 195 minus 5, that's 190, but we have to keep in mind that there's 2 steps that we took to jump through the wall, if this right here is a wall. So that is why we don't check only if the difference is 100, we check if the difference is 102 or greater. And that way we can see for sure if we've saved 100 points or more. And if this is true, if we did jump through a wall and we found that we do save 102 points or more, then we add 1 to the count. And then we keep checking through all of the different grid positions until we've looked in every row and every column. And this should give us all the possible answers. So when we return count and we print it, we will get, let's see, about 1,395. So if we scroll down here, we can see that that's correct. So now for part 2, what they want us to do is instead of just 2 picoseconds or 2 different moves that we have to jump, we have at most 20 jumps that we can do. So we can use less if we want, so we can jump through this wall, for example, and we only use 6, but we can also use more, up to 20 picoseconds. So there's different examples with different jumps amounts. Also, it doesn't matter what path we take. We can see that this took this path and this took the L path, but they both have the same starting and end position, and then we only count this as one different cheat path, because otherwise there would be a lot of combinations of getting from the start to the end, and there would be a lot more different cheat paths that we could take. So we don't need to use all of 20 picoseconds, but we do want to make sure that we save at least 100 picoseconds. And now the answer should be a lot bigger, because we have a lot more opportunities to jump through a lot more walls. So if we look again at the GIF, here's a slow one, we can see that, okay, we're here, and even from the beginning, it's probably less than 20 steps to get to the end directly. So even the beginning path, we can just jump to the end directly and finish the puzzle. So this should have never given us more points on how many paths we can jump through and save more than 100, but now it does. So obviously it's going to give us more correct, more paths that we can cheat through. So you'd be surprised, but part 2 is actually almost the same. The only thing that we've changed is we've kept the initialized distances the same, we've kept the BFS the same. The only thing that we changed is this function here, count cheats part 2. So we also iterate through the rows and columns, and then we skip the walls. But instead what we do is we iterate through how many rows and like vertical and horizontal offsets we can go through, because now, so if we start here, we have up to 20. So we can either go all the way up here 20 times, or 19 times and 1, or 18 times and 2, or 18, 17 and 3, and so on and so forth. So it's going to look a little bit like a Christmas tree actually, because we can go in both directions. And these are all the possible paths that we can sort of take with at most 20. So it's going to be like a rhombus. So if we take at most 20 in this area, if we see that any of the paths, so if the path goes somehow like this, then any of the paths that cross through itself is a path that could be cheaper. So we have to check if the difference is bigger than 102 at any point. So this should take a lot longer to run, because there's a lot more combinations to check. Not a lot more, so the time complexity is still the same because we use a set amount of numbers, but it will take a bit longer to run. So we check row plus direction row, and then column plus the direction column. We also do minus it, and then in the row we do minus minus, and then plus minus. So we check sort of all the combinations and like a I pattern. So if we start over here, then we check the up and then the left and the right, and we check the down and the left and the right. And once we've checked all the possible cheat directions, we check, of course, if it's not out of bounds and if it's not a hashtag where we ended up. So if it is on the path itself, then we check once again the distance. And right now we're not using 102, we're using 100 plus the radius, because the radius in this case was 2. We knew that. But right here we can use less than 20. So what we're doing is we're just adding the radius here so that we know to subtract that, or to add that to the total that we want. And if we do find it, then we add it to the count. So that's another possible cheat solution that we can find. And if we run this, it should take a bit longer to run, maybe a couple more seconds, but it's just because we have to iterate more times through here. The time complexity is still technically the same. And I hope it doesn't take forever while recording, but there it is, 993,178. So if we look at the answer, that's the same exact answer, so it's correct. And now to go through the time complexities of part 1 and part 2, if we scroll all the way down, so we have n as the size of the input grid, and you could either call it r times c, so rows times columns, but I just want to call it n for simplicity. So in this case, the reading the input would be O of n, because we just have to read the entire grid. BFS initialization, it's O of n as well. Traversal of it, in worst case scenario, we have to travel through all of the different paths, and it looks like it is about that, because it does travel through the entire grid as it seems. If we go to the fast one, we can actually see that the blue fills the entire grid. So every single possible place that we can step into, it did. So presumably this is the same for everyone that's doing this challenge, because everyone's input is different, of course. Then we have to check every direction that we can sort of cheat in, and that is n, so how many steps, and then times 4, because it's 4 different directions that we're checking per cell. But since we don't count any 4s, then technically it's not O of 4n, it's just O of n, the most significant digit. That's the time complexity for part 1, and the space complexity is also O of n, so it's pretty good. And now for the time complexity in part 2, it's actually the exact same, even though we have the cheat detection, which we have to go to the outer grid iteration, and then we have to iterate through the radius range and so on and so forth, and then check each cell and the radius. So it's O of 20, but O of 20 is just a number, it's not n, so technically O of 1. So we can, instead of saying O of 20 or something, we can just say O of n. We don't really care about if it's a couple times faster or slower, we just care about how does the program scale with the input of the file. So if the file is 4 times bigger, it means it's going to be 4 times slower. but if this was n squared, it would be 16 times slower. So that's what we really care about, just how it compares to the input file size. And the time complexity is the exact same in part 2. So that was the time complexities. Now, if you guys want to join the leaderboard, I'm going to be leaving the code in the description. And thank you for watching. Happy holidays and see you tomorrow.